Hello. In last two lectures we have discussed discrete Fourier transforms and fast Fourier transform algorithm for it, and what we had said is that a discrete Fourier transform of an n vector, a vector of n elements, can be computed if the following conditions are true. First of all, the domain in which we are working is a ring R, which is commutative, that is to say the multiplication is commutative, and other properties of the rings hold. In addition to that, n inverse should exist, and two, there should be a W which is the nth primitive root of unity, nth root of 1. This should also exist for us to be able to compute a discrete Fourier transform of n component vectors. In addition to that, we had assumed that n is a power of 2 in order to apply FFT algorithm. And in the last lecture I had mentioned that these things are there in the field of complex numbers. So we can actually go ahead and compute the discrete Fourier transforms of vectors where the components are complex numbers. Now today I am going to look at another domain in which we can perform these computations, and that is particularly of interest because there we are going to be dealing with integers only. So today I am going to discuss such a ring which is actually nothing but modulo M ring, where all the M is certain specifically chosen integer, and the ring is numbers ranging from 0 to m minus 1, and both these operations, multiplication and addition, will be done modulo m. So I am going to denote that by Rm. So we will discover this ring in which we can perform this DFT, and for that we will have to establish certain results. So the first one that I want to show is that a power I going from 0 to n minus 1, this geometric series is equal to the product from j going from 0 to k minus 1 a power 2 power j plus 1, where n is 2 power k. So the left hand side, the geometric sum, is a power n minus 1 over a minus 1. So I can factor this and write down this as a power n by 2 minus plus 1 into a power n by 2 minus 1 or a minus 1. So this can be further broken down, assuming that, now of course we have assumed that n is a power of 2. So this is a power 2 power k minus 1 plus 1, the first term. Then we will have a power 2 power k minus 2 plus 1 all the way up to a power 2 power 0 plus 1, and you will be left with a minus 1 at the end over here, which will cancel the denominator. So this is precisely what the right hand side is. The next claim we want to establish is says that let R plus dot 0 1 be a commutative ring. Remember, by commutative I mean the multiplication is commutative. A times B is equal to B times A. N is 2 power k. A is some element of the ring. Then for any p strictly between 0 and n, so this is any integer from 1 through n minus 1. Remember, since 1 is present in the ring, then 2 is also present, 3 is present, so all integers are present in the ring. Then we claim that some a to the power I p for I going from 0 to n minus 1 is 0 mod m, where m is 1 plus a to the power n by 2. In fact, I can state this more generally, and what I really need is in the ring of integers itself. So, even if I ignore this and we generally take n to be 2 to the power k and a is any integer, this is any integer, then again this should hold, where m is 1 plus a power n by 2. Now, let us first establish a small subclaim. If s is an odd integer, then 1 plus x divides 1 plus x power s, where for any x belonging to set of integers, this denotes set of integers. So, to show this, let us divide 1 plus x power s by 1 plus x, and we can write down 1 plus x power s as some h times 1 plus x plus r. This I am treating x as a variable. So, this is a polynomial of degree s, this is a polynomial of degree 1. So, we can always make a division such that this has a degree less than the degree of 1 plus x. So, this has degree 0. So, this is actually a constant. Okay. So, in case if I set x equal to minus 1, then this term is 1 plus minus 1 power an odd power, which is a minus 1. So, for x equal to minus 1, the left hand side is 0. This term is also 0, and h times 1 plus x is 0. Hence, r, which is a constant, must be 0. So, what we notice is that this is 0. So, 1 plus x better divide 1 plus x power s. Now, this is a side result that I will need to prove this claim. So, now let us take the expansion of this geometric series as we have done here. So, sum a power I p I going from 0 to n minus 1 we know is equal to the product. So, I am going to explicitly write down this product, which is a power p times 2 power k minus 1 plus 1, a power p 2 power sorry, this is in the exponent. So, this will be p times 2 power k minus 2 plus 1 all the way up to a power p times 1 plus 1. We have this expansion as we have shown here. Now, let us take let p be s times 2 power t. I can take all the 2 factors in p. So, this will be an odd number. So, this is odd and t. Notice our p is given to be strictly less than n. So, t cannot be equal to k. Okay. Here n is 2 power k. So, t can be anywhere from 0 to k minus 1. This is the possible range of yes. It can be less than or equal to yes, indeed. It cannot be equal to k, but it has to be it can be anything up to k minus 1. Now, let us try and plug this p in these terms. So, the term in which we have 2 to the power k minus t, there will be a term with k minus t. We will get, so we are going to find that a to the power s times 2 to the power t into 2 to the power k minus 1 minus t, k minus 1 minus t, because the largest value is k minus 1. So, t can at most be k minus 1. So, we will have a power s times 2 to the power k minus 1 plus 1 will be a factor of the left hand side. Okay. Now, that means a power s times 2 power k minus 1 plus 1 divides this sum 0 to n minus 1. And now, I am going to use this result. Notice that my s is an odd number, and this result tells me that a to the power k minus 1 plus 1, a to the power 2 power k minus 1 plus 1 divides a power s 2 power k minus 1 plus 1. Hence, a power 2 power k minus 1 plus 1 must also divide this. Now, our m is 1 plus a power n by 2, and this is also a power n by 2. A power n by 2 plus 1 divides this sum I going from 0 to n minus 1 implies this sum is 0 modulo n, because this is m cut. So, now we are ready to describe the ring in which we can compute DFT, and that comes from this result. The theorem says that let n and w be powers of 2 m be 1 plus w power n by 2. Let Rm be the ring of integers modulo m. Then n inverse exists in Rn and W is an nth primitive root of 1. So, these are the two properties we need in the ring to be able to compute the DFT, and we already start with n to be a power of 2. So, we can also use FFT to compute the discrete Fourier transform in this ring. So, let us try and show these two properties. Now, first thing you notice is that n being a power of 2 and m is 1 plus power of 2. So, w power n by 2 is n to the power some alpha. So, I can actually well, I do not need even power. So, I can express this as some alpha times n, because this is a power of 2, this is a power of 2. So, I can boost this to this by multiplying a power of 2, and we are going to get w power n by 2 plus 1 minus alpha times n equal to just 1, and this is our m. So, m minus alpha n is 1. So, if I compute modulo m of both sides, I am going to get minus alpha n is 1 mod m. So, minus alpha is an inverse in Rn. This is multiplicative inverse of n times. So, you can view this way. So, this inverse exists. Now, let us take a look at w. Is it a primitive nth root of 1? So, first thing of course, we notice is that m being w power n by 2 plus 1. So, w power n by 2 is minus 1 mod m, or if you square the 2, you are going to get w power n to be plus 1 mod m. So, indeed it is an nth root. Now, the question is it a primitive nth root, which means that w power, now we want to show that w power p is not 1 mod m for any p between 0 and n. We would like to establish this, and that would mean that w is a primitive nth root. Now, suppose, assume the contrary. assume the contrary. So, there exists a P in the range from 1 to n minus 1 such that W power P is 1 mod m. So, let us consider the sum W power I P from I going from 0 to n minus 1. When you plug in I equal to 0, this is 1. Subsequently, this is still 1 because W power P is 1. So, this entity is 1 for every value of I, and that should become sum 1 I going from 0 to n minus 1, which is n modulo m. Okay. But a little while back we have shown, but we just saw that this sum W power I P, I going from 0 to n minus 1 is expression of 0 mod 1 plus a to the power n by 2 or W power n by 2. So, we had just shown where this was supposed to be an A there. So, we have already shown this result, which is same as 0 mod m. So, these two together, so these imply that 0 is equal to 1 modulo n. So, in this ring 0 and 1 are equal. Now, if 0 and 1 are equal, then this ring you can't have any other term. This would imply that our entire ring is simply just one element. You call it 0 or 1, but that is not what we have. We have actually, this is not equal to 0, 1 to m minus 1. Hence, in this ring 0 and 1 cannot be equal. So, this was absurd. Hence, this assumption is not correct. Indeed, W power P is not 1 for any exponent before n. Indeed, it is 1 for 0. So, we now have shown both these properties which were required for defining DFT are held in this ring of Rm, and we also have a nice property that n is a power of 2. So, we are in a position to define discrete Fourier transforms in this ring. Another interesting property about this is that we can choose arbitrarily large m. The reason is that m is nothing but 1 plus W power n by 2. So, once you decide whatever n is, you can choose arbitrarily big W, and once you have chosen W, you have chosen your m. So, in many computations, when you want to perform exact results, when you want to compute exact results in integers, you can use this ring, but if your m is very large, then you will never cross that domain and you will get exact results. We will see in an example in today and tomorrow's lecture. So, now I am going to discuss the complexity of computing DFT in this ring in terms of bit operations. The reason is we are dealing with now purely integers, and hence we should be able to compute the complexities in terms of bit operations. But before that, I would like to point out one more interesting and very useful property of this ring Rm, and notice that we will often have to compute modulo m of an integers. While we are computing, performing computations in Rm, we will have to repeatedly perform modulo m. Now, m is w power n by 2 plus 1, or w power n by 2 is minus 1 modulo n. Now, let w be 2 power r. Notice we had assumed w is a power of 2. So, we have 2 power r n over 2 is minus 1 modulo n. Now, let us consider you have a number, some number a, and that number is say x0, x1, x2. So, this is the binary expression for number a. So, what we will do is we will split this into blocks. Each block has Rn by 2 bits. And so on. Now, in Rn, in capital Rn, the numbers that we have go from 0 to 2 power Rn by 2, because our m is 2 power Rn by 2 plus 1. So, this is the total span of these numbers. So, the size of the numbers in terms of number of bits can be up to Rn by 2, as big as this. Now, let us suppose the number expressed by these bits is A0 here, the number expressed by these Rn by 2 bits is A1 and so on, A2, etc. So, our number A is nothing but sum Ai 2 power I times Rn by 2, I going from 0 to some number, whatever be the highest exponent here, number of blocks. But 2 power Rn by 2 is minus 1. So, this becomes sum Ai minus 1 power I, 0 onwards. So, this becomes simply A0 minus A1 plus A2 minus A3 in the ring, that is modulo m. So, to compute modulo m, the fast method is just to cut this into these blocks and just take these numbers and subtract this one from this and then add this to the result and so on. So, you just perform this operation, and that is a fast way to compute modulo m. In case this result is still larger than these many bits, which means this result is still outside the rings domain, then you repeat that process. So, we can always quickly compute the modulo m, and this is important because this will be an additional cost that we will have to account for when we determine the bitwise operation cost of computing DFT. Now, let us go back to the complexity of computing DFT in bit operations. Let us go back and recall that the fast Fourier transform algorithm for computing DFT was costing us order n log n in terms of basic arithmetic operations, not bit operations, but adding two numbers, multiplying two numbers, and etc. That was the cost. So now let's go back and recall what were those operations, and from that we will find an upper bound for each of these operations in terms of bit operations. That should give us the bound for DFT. So recall that actually a DFT, that is Fn of a vector, was reduced to Fn of Fn by 2 of half size vectors, and in doing so what we were doing is we were first computing a I plus a I plus n by 2. This gave us one of the half vectors, half size vectors. The other one was w power I ai minus a I plus n by 2. So in the entire process we were computing two new vectors, each of n by 2 size, starting from the vector of size n which was given to us. So each of these operations that we are doing is simply an operation which is linear in the size of the numbers. Okay, we are just adding two numbers. Remember, here we are subtracting, and this multiplication is nothing but shifting, because this is a power of 2. W being a power of 2, this does not really have to be multiplied, we have to only shift it. So the number of operations here in terms of bit operations is going to be at most or Rn by 2 bit operations, bit ops. Now over here again these operations are, these are order Rn by 2 bit operations, and this is in at most this is going to be this is less than or equal to 2 to the power Rn by 2. So once again I am going to perform order Rn by 2 bit operations, which are nothing but shifting, that many shifts. After we have performed this, the number that will result can have at most, and that is in the second case, can have Rn bits, because you are adding this and maybe 1 plus this, 1 plus Rn bits that can result, because here 1 plus Rn bits and here let us say 1 plus Rn bits, Rn by 2 bits plus Rn by 2 bits. And in the computation of DFT, we are actually just performing a linear operation. We are taking the dot product here. So each of these terms is being multiplied to this, and at the end of the day we are adding them all. So we have n such terms that we are adding. So the number that we will have is n times a number of size 1 plus Rn bits, because we will have n such numbers, and this is 2 power k. So that would mean that k plus 1 plus Rn bit size would be the resulting the number that we will get for each of these locations, for each of the components will have that many bits at most. Now that this k plus 1 plus Rn is less than 3 by 2 Rn. So, when we compute the modulo m of this number, we will have at most 3 blocks, and we will be computing this minus this plus this, and the result is still greater than Rn by 2 bits, then we will have to compute one more of these operations. Hence, we have at most 1, 2 and 3 additional operations of summation of these bits. So, in the end, the entire, that is, each arithmetic operation will cost order Rn by 2 bit operations. You can perform the entire DFT by performing n log n operations, each taking this many bit operations. So, the DFT cost order n, there are 2 n's, n square times log of n times, and R is nothing but log of W. So, which is log of W, these many bit operations. The consequence of this is, now we can also determine the cost of computing convolution of two vectors. So, the convolution will cost order. Now, in addition to computing DFTs of two vectors, in the case of convolution, we also had to compute point to point multiplication and then compute inverse DFT. Now, inverse DFT and DFT cost the same. So, this will be the cost of all the 3 DFT operations. Now, in addition to that, we have to add the cost of m multiplications of numbers of size Rn by 2 bits. So, that will be n times m, Rn is n log W plus, this will account for those computations, and this term n square log n log W. So, convolution in Rm will cost this many bit operations. In case we are computing in this ring the multiplication of 2 polynomials, then it will cost us this many bit operations, because polynomial multiplication is nothing but the computation of convolution. So, finally, one more remark. In case we have a polynomial, suppose we have p of x and q of x, and the coefficients of these polynomials are in the range 0 to W power n by 4 divided by square root of n. Let us consider a situation where the coefficients are restricted to this. In that case, the largest number that will result when we perform the multiplication of p and q, p times q, in this computation we are going to perform effectively the convolution of these coefficient vectors, and in doing so what we are going to do is we are going to multiply 2 numbers in this range and then add those n such numbers. So, each component of the convolution vector will be in the range 0 to the square of this times n, and that will be w power n by 2. Now, this indicates that if my coefficients are limited to this, then I can perform the same computation in Rm. So, we can perform the computation P times Q in Rm. The reason is, in Rm these values will not change, they will remain as it is. So, we can get exact value of these two, of the product of these two polynomials when we perform computations in Rm. So, these are the observations about the complexity, and of course, one remark about how far we can go without losing any information. Now, we are going to just give some initial remarks about an interesting algorithm for computing algorithm to compute product of two integers of n bits each. Now, first of all, let us recollect that the trivial algorithm, that is the first one, is the trivial algorithm, the long head algorithm, in which all you do is you take each bit and multiply to the n bits of this thing. So, we really end up adding n numbers of size n, and adding n numbers of n bits, we are going to take order n square bit ops, because each summation takes order n time, and there are actually n minus 1 summations, because there are n numbers. But we can do something better without much of an effort, and this idea that we are going to present is very similar to the idea we had shown coming from Strassen in matrix multiplication. So, let us take the number A, which is n bit number. So, let us actually split this into 2 n by 2 bit numbers, okay, and this I will call as number A0 and A1, which simply means A0 plus 2 to the power n by 2 A1. Similarly, we will have B0 plus 2 to the power n by 2 B1. Both all these numbers A0, A1, B0 and B1 are n by 2 bit numbers. Then A times B is A0 B0 plus 2 power n by 2 A0 B1 plus A1 B0 plus A1 B1 times 2 power n. Now, consider C equal to A0 minus A1 and D equal to B0 minus B1. So, these are also only n bit numbers, n by 2 bit numbers. So CD is nothing but A0 B0 plus A1 B1 and minus A0 B1 plus A1 B0. So what you notice is, if I compute this product and this product, I get this immediately, and you plugging these three values here, we are getting the entire product of A and B. So the total time complexity of this operation is some constant C1 times n, because we have certain linear operations in time. We are just subtracting and adding and all. So we are performing three operations of size n by 2 and some linear operations. Hence, we will get T of n to be n to the power log base 2 of 3. So we can very quickly improve this exponent from 2 down to log 3 of 2. But this trick does not take you much further than that. And now we are going to discuss in this and the next lecture something called Shonaz-Strassen integer multiplication. Schona, Shonaz-Strassen integer multiplication. Algorithm. In this algorithm, we are going to use two key ideas that we have discussed earlier. The first one is Chinese remaindering, and second is, of course, use of DFT. Use of DFT in modulo n ring. In this algorithm, what we will do is we will compute the product, that is to say we have A times B to compute. This quantity we will compute in modulo P1 and in modulo P2 rings, which we hope to do more efficiently than directly computing this. And then we are going to use Chinese remaindering to get A times B modulo P1 P2. We will choose P1 P2 which are coprime. So this will be the core of our idea, and we will choose our P1 P2 in such a way that we can use this RM ring that we have discussed. So that would be in the next lecture. So I hope to finish that lecture, this algorithm in the next lecture.